What am I doing? Okay, here we go. So today dovetails directly into yesterday, directly into the stoichiometry of enthalpy changes. Remember when we said enthalpy change, we're talking about what? What is enthalpy? What's enthalpy? Yeah, dynamic. Sorry about that. So what is enthalpy? Relates to heat. Definitely relates to heat. Good. Very good. So it's the total internal energy of a compound. And enthalpy changes when we do what? Fair enough. Specifically, reactions. Enthalpy changes when we undergo reactions because what? What happens? Heat changes, definitely. Why? What inside the chemicals is making the heat change? Yeah, what about? Where did we say that energy is stored normally in chemicals? Yeah, what part of them?
The electrons.
The electrons. Specifically, some of that is internal and is going to stay, but all those valence electrons are involved in bonds. Very good. And when we undergo chemical reactions, bonds are breaking. Try that again.
Bonds are breaking.
Bonds are breaking. When we undergo chemical reactions, bonds are broken and new bonds are formed. Duh. Well, it's going to be a long period. I apologize in advance. So as we undergo chemical reactions, there is less or more energy in bonds, right? Does that make sense? And that has a predictable change in enthalpy. So all through the last bunch of days, we've said for this reaction, we know that for every mole that goes through, this much heat will be released. Or maybe for a different reaction, this much heat will be absorbed, right? That's what we've been talking about. I can give you a molar enthalpy and say, for every mole, 100 kilojoules is released. And you can then use that information to work with a specific reaction. If you say, okay, for every mole, 100 kilojoules gets released, what if I had 2 moles? How much energy would be released?
Double the amount.
Double the amount. So if it was 100 per mole, it'd be 200 kilojoules. Does that make sense? And if I reacted 5 moles, how much would be released? 500 kilojoules. Good. Today, we're going to talk about the natural conclusion of that, or the natural consequence of that. So I put a quote on here. There are many ways to climb a mountain, but the view from the top is always the same. I like that quote. But to get a little less esoteric, let's say that, hypothetically speaking, I challenged Mr. Calford to a contest of athletic prowess.
Do you really want it?
Oh, yeah.
Either of you really want it?
I'm going to go with no. I suggested bacon eating contest. He said, no, that's not athletic enough. I said, what if we ate so much bacon that we were really sweating? He said, no, that's still not athletic enough. So we agree on a foot race. We're going to run. No.
You're only going to run 1 foot.
No, so I challenge him to this race, and I say, okay, and so we both train, and I show up in my tracksuit, and I got my headband on, and my armbands on. I'm ready to go. And we go to the track. Where's a track in Welland? I've never noticed one.
The one right there.
But is it? But I'm talking one of those nice. Do you have
It is Welland. Don't expect anything.
Does Centennial have one one of the rubber matted ones? Because my high school never had one, so we always had to get on a bus and go to West Park because they had a nice track. Okay, so yeah, so I'm not slumming it here. I want the rubber padded. I like some cushion support for my ankles when I'm engaging in feats of athletic prowess. So we go for this race, and we just said, okay, we're going to run around the track. Whoever gets to the finish line, least amount of time, wins. A fairly basic race, yes. This is standard stuff. So, they shoot the gun, the gun, and Calford takes off he's booking it. And I sit down and I get my submarine sandwich, which I brought with me. I eat my submarine sandwich. It's delicious. He gets to the end, and I, of course, being generous, admit that I won. Clearly, I won. Why did I win?
You're already in it.
Yeah, because I got to the end first. Right? He did all this running,
You
and I
walk
got
back
to the
2
end.
steps.
Sorry?
You walk back 2 steps.
That's right. I just took a step back, ate my sub, happy camper, right? In other words, if the race hadn't been set up with the condition that you had to run all the way around, if all that matters is where you end up, I won the race, right? And today we're going to talk about something kind of similar to that. We're going to look at how the outcome of a chemical reaction, the final outcome, is the important thing. And whatever steps you follow in the middle are really, energetically speaking, irrelevant. And I'll explain what I mean by that. A better example might be this. Imagine a bike that has exactly 0 friction, such that, you know, if somebody gave you a push, it just keeps going at perfect speed. You know, somebody pushes you, so you're going 10 kilometers an hour. Now you're just going that speed and you're never going to slow down. No wind resistance, no rolling resistance, no friction in the gears, anything like that. If you came to a hill that went up, you would have to
Increase the elliptic speed.
yeah, you'd have to pedal, right? Even though the bike is already moving, to avoid stopping on the hill, I'd have to pedal, right? But when I got to the top of that hill and came back down it, what would happen?
Gravity would take you and you go faster.
Gravity would take me and I would get all of that energy back. Does that make sense? And if I went down a hill, I would speed up, right? Because gravity would pull me down. But then when I went to go back up that hill, what would happen? I'd slow down again. And assuming that the 2 levels were at the same height, when I got back to the top, I'd be going the same speed I had been when I started, right? And the physics you do in high school is all physics like this, right? Because we ignore all of these imperfect considerations like
Rocks in
wind
the way.
resistance and rocks in the way and snakes that scare me and things like that.
Liability.
Chemistry, in principle, works in the same way. We can do a bunch of reactions, some that release heat, some that absorb heat. But in the end, the question is, if we released this big amount of heat and then reabsorbed that amount of heat, the actual net amount of heat released is just the difference between them. Does that make sense?
Who burns diamonds?
So we'll talk. So you can. Burning diamonds is not something I'm going to demonstrate for you because it's an expensive little demonstration. But you absolutely can. You get enough heat, a diamond will burn. Because diamonds are made of carbon. Carbon. So when you burn a diamond, what are you going to get? Carbon dioxide.
Who's the best friend?
Yeah, that's
You
what
said second, so who's the best?
Wouldn't you like to know?
Yes, we do.
My best friend's name is
Hydrogen.
Greg. He's a nice guy. I don't know what else to tell you, really.
And how
It's
come
just-
diamond is speaking
We met in high school. I don't know. So
this just says a chemistry.
I'm not a chemistry teacher.
It doesn't mean specifically.
You were actually our math teacher first, so
I'm not a
Yeah.
math teacher. I'm sorry to tell you this because you all had me for a semester as a math teacher, but I am a sham fraud of a math teacher, just desperately trying to keep up. And I apologize for all of you who are subjected to it. Now, let's move on.
Sam said he'd seen himself.
Yeah. Sorry? Oh, yeah.
We forgot that thing.
No, only because I came.
Oh.
Allow me, Zach.
So you just had a
Is there anything else I can get you?
Sandwich.
A sandwich, coffee?
Yeah.
Okay.
Maybe
Some
the
diamonds.
onion there?
That's some diamonds.
Diamonds. Okay. So let's talk. Suppose we want to know how much energy was required to turn pure carbon in the form of graphite. I said called graphite, but really in specifically the form of carbon called graphite into diamond. All right. What chemical equation would that follow? It's sort of a trick question. What are we starting with? In the form of? In the form of graphite. And we are turning it into in the form of diamonds. That's all. That's all. Having said that, if it's that easy, why aren't I making a fortune making diamonds with my chemistry knowledge? What do we need to make this happen? How do diamonds form in real life? Yeah. Yeah, what is required is tremendous amounts of heat and tremendous amounts of pressure. In fact, this is a possible chemical reaction, but it's a pretty challenging one. Under normal lab conditions, making diamonds isn't practical. There are different techniques. The natural one is lots of pressure, lots of heat, lots of time. I found one method that uses high explosives to provide heat and pressure and then requires 3 days of boiling in concentrated nitric acid. Yeah, so I ran that by lab safety at the board, and they were like, no, Nazis. So
We don't have to do it in here.
Yeah,
Just put in the fume hood. It always
our ventilation system works so well. What could possibly be the problem? So we're not going to do this lab. Now, the fact that I can't physically sit down and turn graphite into diamond, does that mean that I can't know how much energy it would take to do that? For the record, my instinct would be like, yeah, that's right. Like, you would have to do it experimentally to know the outcome. Even when you go look in a textbook and they show you the molar enthalpies for things, how much energy is released or how much energy is absorbed by 1 mole of a reaction, they have gotten that experimentally. Somebody has sat down with the chemicals, done the reaction, measured it, just like you're going to either Friday, but more likely Monday of next week, do a calorimetry reaction. But what Hess's law says is this. Just like that bicycle rolling down a hill and then rolling back up a hill, we could say, okay, I can't do this reaction. It's not practical. But I could do 2 different reactions that will end up being able to tell me about this reaction. So what are the 2 chemical compounds involved here? There's only 2.
Graphite and diamond.
Graphite and diamonds. Now, there are 2 of these that I can do quite easily. The first is burning graphite. I could take that graphite, just like in your pencil, and I could burn it. And it tells me here it has a delta H of negative 394 kilojoules. Exothermic or endothermic?
So
I've got endo, exo, exo, still stuck on that E on the fence. Well, first of all, a negative delta H means the energy in the molecules is going down. And if the energy in the molecules is going down, where is that energy going? Out to the surroundings. So it must be autothermic. That's right. Exothermic. Really, autothermic would be a better name. We would understand it. But anyway.
Well, would the contrary be endothermic?
Yes, which also sounds awesome. All right, so this reaction would look like this. Graphite plus, when we burn something, what are we reacting it with? Yeah, which is O2. It is a gas. And this is going to yield what? Come on, team. What's it going to yield? No, it's definitely not going to make a diamond. Come on, you burn carbon. What are you going to get? Very good. You're going to get carbon dioxide, which is a gas. And you're going to get what? You're going to remember that the delta H is negative 394 kilojoules. Did I use 1 mole of carbon here? So do I need to double this or triple this or anything? No. If to balance this, I'd had to put a 3 here, what would I have to do with this number? Multiply it by 3. But in this case, I didn't have to, right? Does that make sense? Cool. All right. What about burning a diamond? Who can tell me what that reaction will be? Oh, no, carbon. Diamond. Okay, diamond plus oxygen. Yep. Very good. And what should I add to that? Great. And again, we're not going to put mole because we know how many moles we used. We used 1. And again, if I had to put a 7 in here to balance it, what would I have to do to this number? That's right. In this case, 1 balances it, so we're good. Now, here's my point. All the information is in here to actually tell us how much energy it takes to make graphite become a diamond. Chemical equations are equations. That makes sense? We call them balanced chemical equations. And even though, and it was actually interesting that Jade made a slip that we all make all the time. I know I make it all the time, where instead of saying yields or reactive form, she said equals, right? But that's actually true. The left side does equal the right side in every way. There's the same amount of carbon on the left as on the right. There's the same amount of oxygen on the left as on the right. And now, for the first time that we're doing thermochemical reactions, there's as much energy on the left as there is energy on the right. Because even though graphite and oxygen contain more energy alone than carbon dioxide does, to make this thing balance in the thermochemical equation, we also throw in the fact that there's an extra 394 kilojoules of released energy on the right side. Does that make sense? So it is true that the left side of this is in fact equal to the right side of this. Does that make sense? If they're chemical equations, then just like any other mathematical equation, we can algebraically manipulate them. Does that make sense? We can use algebra to manipulate chemical equations, just like we would use algebra to manipulate mathematical equations, because a chemical equation is a mathematical equation. It is telling us that the amount of atoms and energy in carbon and oxygen is the same as the amount of matter and energy in carbon dioxide and an extra 394 kilojoules of energy that gets released. This is equal to that. And then this equation is telling us the amount of energy in diamonds, a mole of diamonds plus a mole of oxygen, is equal to the amount of energy in a mole of carbon dioxide and the amount of matter in a mole of carbon dioxide, if you make sure to account for an extra 396 kilojoules of energy that gets released. Does that make sense? Tell me if it doesn't, because it's important. You may be shocked to know this. I have a history of not making sense the first time I say this. Does that feel comfortable for everyone? Okay. Here's what we're going to do then. We're going to say, could I algebraically manipulate these two equations so that I end up with the equation I want, which is graphite becoming diamond with some delta H that I'm interested in. I'm curious to know what the energy change is when I make graphite into diamonds. Can I manipulate these two equations to make that happen? It is. How do I, you're totally right. How do I make that work mathematically? Because that's going to work easily when there's only two equations and they're simple. Now we're going to get to questions where it's more complicated, though you're totally right. In this case, because there's only two, it actually is just the difference between them, which is a great insight. You're right. But what we're going to say here is this. The equation I want, in the end, has what on the left side? On the left side. Graphite. It has what on the right side? Diamonds. Good. Good. This equation here has graphite on the left side. So it's good for me. What about this equation here? The diamond is on the left side, but in the equation I want, the diamond is on the right side. Okay, no problem. Burning diamond to make CO2 releases 396 kilojoules of energy, right? Could we do that reaction in reverse? Could we, in theory, break carbon dioxide apart and take the carbon we get and turn it into a diamond? Yeah. Sure, you can always do it in reverse. If we did that, what would the enthalpy be? Bingo. That's exactly right. So this reaction would be useful to us, but we need the reverse of it. And so what we're going to do is we're going to write these equations one on top of the other, but we're going to, if we need to, reverse them. In this case, I want to reverse the second one, and I want to leave the first one how it is. I am going to number these just to kind of keep track of myself. So I'm going to line up the yield signs on them, because that's kind of a helpful little habit of mind. So I'm going to say that graphite plus O2 yields CO2. And I'm going to say the delta H is negative 394 kilojoules. And then in the reverse of 2, what am I going to say? CO2? Oh, so I'm just going to write it here, right? CO2 yields O2 plus diamond. And I should have mentioned that that was a gas. And the delta H would be now very good, 396 kilojoules. And what I'm going to do with these two equations is I'm going to add them together. I'm going to sum them. If these are indeed equations, then the laws of algebra must apply, which means I can add these two equations together. And we're going to do something here that we will never do again. This next step is kind of a step to show you why it works, though in the future you would skip it for sure. What all do I end up with on the left if I add these two equations together? On the left. Close. Carbon dioxide, oxygen, and good. So I would start with graphite. And I would have the O2. And I would have the CO2. All from this side. Does everyone see where those came from? All right, what would I have on the right side? Yeah. And lastly, what do I need to calculate? If I added up the equations, I also have to add up. And negative 394 plus 396 is what? 2. Now, what do you notice about this equation? Just like in math, what would you notice about this equation? Yeah, Kevin. That's right. If I have oxygen on the left and oxygen on the right, in this particular equation, is that oxygen doing anything or changing? Let's get rid of it. What else? Carbon dioxide and carbon dioxide cancel. And what remains? Well, graphite becomes diamond. And the delta H is just 2 kilojoules, which, by the way, is not a ton of energy. The actual process of making graphite into diamond doesn't require a ton of energy. The problem is the catalyst required, the amount of energy required to make it happen. The actual net energy input, not huge, 2 kilojoules per mole. It's very, very, very doable. The problem is to make the reaction favorable, which we'll learn all about next unit. What makes a reaction want to happen versus not happen requires a lot of finagling. But there we go. Does that make sense? So that means on net, if I turned graphite into diamond, it would require only 2 kilojoules of net energy. Now, I'll tell you right now, the actual steps would mean first you'd have to put a bunch of energy in, then a bunch of that energy would come back out. Does that make sense? But the overall net would be just 2 kilojoules for 1 mole of graphite becoming 1 mole of diamonds.
So this is
That's right. So this process of figuring out the enthalpy change of one reaction using other reactions was pioneered by a gentleman by the name of Hess. His last name was Hess. I don't know his first name. I should look it up. And so we call this Hess's Law. Hess's Law. There is some scholarly debate of whether Hess's is best written thusly or like this. To me, both look awkward. The second looks a lot less awkward. So that's what I go with. You can do what you like. Hess. I always feel like saying it in like a really like Voldemort voice. But anyway. Has to be what? Just C Hess? Oh, I thought it was gonna be like C Hess run, okay. Yeah. Yep. Does this basic process make sense? I have two equations. I know the delta H of those equations. I have a third equation that I want to figure out. I don't know its delta H. I can take the two that I know and algebraically manipulate them to give me the equation I don't know. Do you feel like you can try one? I think you can. I have faith in all of you. All right, so here we go. On the next page, I want to know about this reaction. Taking nitrogen gas, reacting it with oxygen to make nitrogen dioxide. I don't know its delta H, but I want you to use these two equations to make it happen. Okay, follow the same process we did on the previous page. Give it a crack. I'll come around and say encouraging things. These are tricky at first. This is tricky stuff, but they're like little puzzles. And they're very rewarding when you get to the end one. I think. Your mileage may vary. That's just you. That's so sad. Can I confess something? Like maybe one of those like little wooden ones as like a little kid, but like in my living memory, I do not have the patience to finish a puzzle, and I never have. I feel a little bit ashamed of that. No. Yeah, it's called Hess's Law. It's true, but I mean like the little paper things cut into shapes. Oh, good.
Okay, I want to know what one is.
So what you have to ask yourself is look at this and just say, what do you want on the left? And a good rule of thumb, ignore things like oxygen, because oxygen is always just normal. But here, what do we have on the left? And 2, right? Okay, so look here. Does either of these equations have any 2? Great. Does that have it on the side you want, or do you have to flip it? Perfect. Now again, we're going to ignore oxygen. We're going to trust that oxygen will just work. Things like oxygen and hydrogen, that's just root. Now, NO2, what side is it on? Okay, but on this one. That's right. So you want to match these things. And again, rule of thumb, ignore oxygen, ignore hydrogen, ignore water. Those kinds of things that are so common. If you've done it right, they will work. Focus on kind of the weird stuff. How we doing? Take step.
I feel like
You might miss it. Let's take a look. Oh, golly. Okay. Ooh. I've been, so this is time of year, I've been walking again. And since I broke my foot. And the old legs have not been appreciating my newfound commitment to my health. And they are rebelling. And that was one of the most painful things I've ever done. Was just kneeling down right now. I'm wishing for death right now. So that's okay. The trick is this is okay. And my advice is ignore water. It will work it. Ignore things like oxygen. Yeah, focus on kind of strange molecules. They're not usual stuff. Now like hydrogen, oxygen, water. They're just another common stuff that ignore them. Here I see two things that are not. I see energy and I see energy. So energy on this equation, what side is it on? Left. Cool. So we know it's the one and two on the left. Now, which of these equations does it show up? And what side is it on here? So it's good. So we definitely do not want to flip it. That's like a thing.
Oh, this is, okay, see, I thought that was another.
Ah, yeah.
That's it, okay.
You got it? Cool. All right. Oh, that's okay. Wow. I want you to write it out nice and finely with an page. Right, like you cross all these out. What did you get?
That's the final. I should have a box around this.
Okay, that's cool.
That's my bad.
No, that's okay. That's beautiful. I got it.
One thing box around.
But yeah, I mean, that was it. Indicate to yourself somewhere.
Actually, very important. If I got another box in that shape, weird pens, with possible.
I mean, if you actually look at the cardboard box, it's probably closer to that than actually straight.
That's
Like, that's what you have it by the time it's got like been through shipping and it's got tape all over it. Yeah.
Essentially,
After light through a box from the
You know, like, when you put it that way, it makes it sound a little pathetic.
Thanks, Mike.
Um,
I didn't need any more. So you put that in the
Man, just give me advice, like, pick out pages next to it as you go. That way when you have these together, you can try and.
Nice.
Okay. Well done. And how's that feel?
Oh, good.
It makes sense,
I
right?
forgot that I had to like. Yeah.
Right.
It's not on the way.
Yeah, very good. And how's that feel for you?
I feel like I had my
Can I take this up without rushing anybody? Can we, is that fair? I take a look. Well, you added all these together, so add these 180 plus negative 100 plus.
Basically.
Yes, like absolutely.
I don't know how I forgot it.
That's okay.
So I did have a
Okay, so I want to talk our way through this, and even if you have it done, and even if I told you you're right, follow along with me just because I'm going to give you some pointers as we go, which may be helpful. My advice when you approach a question using Hess's Law is to look at what I kind of call the target equation. This is the chemical equation that I'm interested in, whose delta H I do not know. And I'm going to try to make that target reaction, that target equation, using these two. And so in my mind, ignore water, ignore oxygen 9 times out of 10. That's your best approach. Anything that isn't water or oxygen, kind of highlight and take a look. So I'm going to say, okay, N2. What side of the equation does N2 appear on here? True, but in this equation, what side of the equation is it on? Left. And then I'm going to look down here and try to find this. And if it's in both equations, move on. Trust that it will balance out. You want to look for things that only appear in one of the equations you're using. In this case, N2 appears only in this one. And in the top one, it's on the left side. In the bottom one, it's on the left side. Do I need to change equation A? It's got what I want. It's got N2, it's got one of them, and it's got it on the left side. Everything is where I want it to be. Does that make sense? So equation A is just going to stay how it is. Next, like I said, skip O2, because what do you notice instantly? These both have O2. You could think about it and say, well, I want them both on the left side. To me, better just to skip things like that. But this, 2NO2. Do we see that in this? And you got to be careful because this is 2NO, this is 2NO, but this is 2NO2. This matches it. It's gray. It's a light gray. It's a very, I think, elegant way to highlight.
Looks like white.
Okay, so like it can't be the same white. It's got to be less white than mother of pearl. Do people still watch the Celebrity Jeopardy Saturday Night Live skits? Have you ever seen these? It's just riffing on the fact that Celebrity Jeopardy always consists of really easy questions because they don't want to make the celebrities look stupid. So the highlight of it is, so on the Saturday Night Live version, the questions are ludicrously easy and nobody ever gets them right. And my favorite one is, tonight's categories include, and he lists them all, and the second to last category is colors ending in Urple. And so then Keanu Reeves goes, I'll take colors ending in Urple for 100, please. And then Trebek says, this is the only color ending in Urple. And Keanu Reeves goes, what is light Urple? And I find that really funny. Anyway. Never mind. So here. Shh. Okay. Nitrogen dioxide. What side of the equation is it on here? Very good. Down here, what side of the equation is it on? Left. So what do I have to do? Yeah, I've just got to reverse this one. And once we know that, this becomes a trivial question. You're just going to rewrite these. We're going to say, and you will eventually skip this step where you rewrite both of them, and I get that. Does that make sense? Like, you're going to learn to start skipping steps here, so every one of these doesn't take like 6 pages to do. As long as you do it well, I'm okay with it. For now, we are going to write it out every time. That's right. So there's my first equation. How am I going to write my second equation? Yep, so what's it going to be?
O2 gas plus 2NO gas yields 2NO2, which is also.
Great, and the delta H on that particular reaction will be what now? What did we do to it? So its delta H will be? Very good. Negative 112 kilojoules. Don't forget that. If you reverse the reaction, you have to reverse the delta H, right? If this reaction absorbs energy, its reverse will release energy. And now when we go to sum these, I'll already show you a step skipper. I would just cancel in the addition line here. So I have 2NO on the left. I have 2NO on the right. Bless you. Those cancel. Does anything else cancel? No. And what do I get? Yeah, and I should, sorry, I'm being lazy with my state demarkers there. I will get dock marks, and I don't like getting dock marks. So let's I'll be nice and careful. And on this side? Very good. And the overall delta H of this reaction is 68 kilojoules. Because, bless you, because just like I added all the reactions together, I summed the delta H's. Sorry, pardon me. And one of them is positive and one of them is negative. Questions about that? Okay, we'll do one more together, then I will set you loose to do this. The last skill we need to learn is this. This one, now we're getting down to a bit of mystery here. I want to know what it takes to make, what is C4H10? All y'all? Butane. I want to know what it would take to make butane by taking solid carbon and mixing it with hydrogen gas. Now, spoiler alert. Do you think we make butane by taking solid carbon and mixing it with hydrogen gas? Yeah. I mean, are you realistically going to mix these two things together and they just happen to decide, yeah, we're going to make butane. Not propane, not methane, not ethane, not anything else. The only thing we're going to make is butane. Is that a realistic, is this the organic chemistry ticket to my butane needs?
You believe it.
If I believe hard enough.
And then watch if you say CC again, we said nothing.
I heard
Paul Boat Malcop to the office, please. Paul Boat, comma, Malcop, comma, to the office, please. Okay, so this reaction is not one I can actually do, which means that I could never measure its delta H directly because it's not going to happen. By the way, this symbol here, we will talk about more tomorrow. This just means standard conditions. And all I mean by that is reactions can be affected by temperature, pressure, and all those things. Standard conditions, of course, you know what temperature and pressure that is. If you recently took grade 11, if you didn't, don't worry about it. That's all that means. You don't need to worry about it now, but it means a pressure, an atmospheric pressure of 101.3 kilopascals. And temperature? No. 0 Celsius, 273.15 Kelvin. Anyway, don't worry about it for now. But that's all that symbol means. Just it occurs to me that I haven't mentioned it yet, but there you go. Okay. We want to figure out what the delta H of this reaction that would never actually happen would be based on these reactions that do happen. All right? Does that make sense? So I can absolutely burn butane. May not be able to make it this way, but I can burn it. I can absolutely burn carbon, and I can absolutely burn hydrogen. Does that make sense? And using these three reactions, I can make this reaction. And what I want to do is follow the same steps. But this time, we're going to note a problem. So we're going to look at this and play the same game we played last time. This 4 carbon. In this reaction, where do I find it? On the which? Left side. Very good. So there it is on the left side. Where do I find it down below?
On the left side and B.
Good. So it's perfect, right? I can just use this?
No.
What's the problem?
There's not 4 of them.
There's not 4 of them. So what do I have to do with this? I have to multiply it by 4, which means everything is going to be quadruple. Does that make sense? I will now have 4 carbons. I will have 4 oxygens. I will have 4 carbon dioxides, and my delta H is going to be this times 4. So let's go ahead and write this down and just get it out of the way. 4 times B. I'm going to write 4 carbons plus 4 oxygens. Oh, we don't typically put the 2 in brackets now, do we? Yields, we do not. 4 CO2. And can somebody please tell me what the delta H for that will be? Negative, right?
Yes.
Negative 1574, and that's 0.0?
Yep.
Perfect. Questions about that? Does that make sense? Why did I quadruple everything?
Because that way you have enough hydrogen.
That's right. Okay, what do we want to deal with next?
C, so we have the hydrogen.
I want to understand whether water is gaseous or liquid.
It can be either. In this case, it is gaseous because when you burn something, it requires a lot of heat. So when you burn something, the temperature is typically high. And if water is at a high temperature, it is gaseous. Does that make sense? So water, and this reaction would have a different delta H if it were making liquid water. And realistically, that's a reaction that won't happen, though you could figure the delta H out of it if you wanted. Okay, what do we want to take care of next? We've taken care of 4 carbon. We've got them where we want them. What next? Hydrogen. Hydrogen's going to suck. Not going to be fun, but we're good. We are clever folk. Hello.
Because I never see you.
No problem.
And you know we're voting today. I don't know if
Yes.
you meet in the staff room.
I don't normally, but I'll come join.
You will come.
Yep,
to the
I'll come
staff
join.
room?
Yep.
Okay, now we're cooking. Literally boiling water. You see it?
See ya. I enjoyed every moment. That was wonderful. All right, how many hydrogens do we need? 5. Man, this sucks. And I need them on what side? Left. Here's the deal. We're dealing with moles. For the purpose of this, how many do we have here? What do I want to multiply this by? 2.5. You can do that. That's okay. Yeah. I'm gonna say 2.5 as 5 over 2 because I like fractions. If you'd rather say 2.5 times, totally cool. Yep, I'm okay with that. All right, so we're gonna have 5 over 2 times C. What's that reaction gonna look like? Tell me, what do I get here? Would it actually stress you out less if I made this 2.5? This is the only time I'm going to write it as a decimal, but for now I'm going to write it as a decimal. Okay? So let's go here. What's 2.5 times 2? So how many hydrogens do I have? So we have 5 H2s. Good. What's 2.5 times 1? Yeah, this one I am going to write as a fraction because you can't put a decimal in a balanced chemical equation. All right, so you can use decimals everywhere it ends up as a whole number. Totally cool. I have no problem with that. You can use 2.5 for the delta H, but I'm not going to put a decimal in front of an O2 because I can feel in my soul my high school chemistry teacher hunting me down and beating me up for doing that. All right, and I don't want Ron Chappell to beat me. All right, I just don't. So, Ron Chappell, he was a great guy.
Are you saying that because you get a knife over your throat?
Just because I was scared of him didn't mean I didn't think he was great. Okay, and what is 2 times 2.5? 5. So we have 5 waters. And can somebody please tell me what the delta H will now be for this reaction?
It's negative 1209.
1209 decimals?
No.
Really?
Yeah. I did it on this calculator.
Oh, okay, perfect. I trust you. I'm surprised.
It doesn't say 0.0. It says
You don't check
0.09.
your equations when you make them.
Sorry?
You don't check your own equation.
If you're asking if I go through the whole sheet and do it, I do. If you're asking if I then memorize all the numbers, I do not. Okay, and The last thing we want to do is we want to keep going through our equation. There's only one more element to it that we need to look at, and that's this C4H10. Which side is it on up here? The right. Where do I find it down below in my 3 equations I'm using? Yeah, it's in this one on the left. So what am I going to have to do with equation 1? Reverse it. So can somebody please tell me what I'm going to write below for the reverse of A? What should I be writing? Yeah, sir.
All right, so you're writing 4 CO2
Okay.
plus 5 water.
Okay, yep. And those are both gaseous, right? Okay.
Yields C4H10
C4H10. Great.
plus
That's okay. And that's it?
and then you also have
And what's my delta H for that? And I'm going to, guys, if you didn't leave yourself enough room, I encourage you just to highlight these delta H's. Just kind of slide them over a bit like that. You know, just make sure you've got room. That's all I'm saying.
because we're going
Just
to
like
do that on
that.
our page.
Yeah.
And then drag.
You might even want to drag them down and shrink them in size a bit if you made them too big. Just think about that. You just have to press, don't forget the button on your pen. That's the key. Okay. What's the delta H on this?
It's going to be positive.
Cool. And then obviously, what am I going to do with these 3 reactions?
Combine that.
Yeah, I'm going to sum them all up. Now that I've done the hard work of getting them all where I want them, we're going to sum them. And first things first,
We've got a problem.
do we?
You don't have enough oxygen.
Well, let's take a look. So let's start with what we can cancel. What cancels here? The 5H2O and 5H2O cancel. Anything else cancel? 4CO2 and 4CO2. Okay, now let's take a look. Do I want any oxygen in my equation? No, I want there to not be. It is tempting to just assume they cancel out, but we should actually check. So I have 4O2 up here. Hey, if I were going to write this as a fraction over 2, what would it be? Like 4O2 is the same as saying how many O2s? 8 over 2. Okay, so if I cancel those, I cancel 8 of these, right? Does that make sense? Which would leave me with how many? 5. Okay, so now I have 5 over 2O2 on the right, and on the left, 5 over 2. Now look at me. Look here. If you would rather just plug 4 plus 5 over 2 into your calculator and see what it is, do that. You'll get 6.5. Does that make sense? And then over here, if you just want to do 13 divided by 2, you'll get 6.5. I don't care how you show that that's the same amount of oxygen. Just make sure you know that it is. Does that make sense? Did that go over people's head? Fractions stress people out. Okay, let's try this. Let's try this. I tried so hard not to erase that O, and yet it went. Let's try this. This 5 over 2, what is that as a decimal? I would never write a decimal in my balanced chemical equation, right? But if I were going to write 5 over 2 as a decimal, what would it be? 2.5. So altogether, how many O2s do I have over here? I have 4 and 2.5 for a total of 6.5. So 6. Oh, I wanted to use green for this. Hello, green. That's a really big, thick pen. Okay, so 6.502 altogether. Does that make sense? Over here, if I divide 13 by 2, what is that number? 6.5 O2s altogether. You do not need to show me this step. I'm just showing that 4 and 5 over 2 does in fact equal 13 over 2. It is helpful if you're strong with your fractions, but we don't need to be. We can get through it. Long story short, 5 over 2O2 and 4O2 altogether is 6.5. 13 over 2 is 6.5. Those cancel. Does that make sense? Tell me if it doesn't. I can try again. Does anyone want me to draw the pizza slices up on the board? I haven't taught fractions in a while. Can I tell you something? I taught grade 9 math for the first time last year. Teaching fractions is actually really challenging. Like, how do you explain dividing fractions in a way that intuitively makes sense to people? Like, I can tell you how to do it. Flip the second fraction, make it multiplication. Why does that make sense, Mr. Orlando? Wow. Wow. When I was in grade 9, my math teacher said to do this. And so I've been doing this for like 2 decades now, kid. And it just has always worked. You know what I mean? And so well, but I don't understand it. And then you're like, do I understand it? Or have I just been doing it? I understand how to use it. And it's rare that I come across something in high school science that I feel like I don't actually understand. Because, you know, and even in high school math, like I have a pretty intuitive grasp. And here I am reviewing grade 6 math, and they're like, well, why is it working? It works. Just do it. Just shut up, kid. Just shut up, flip the second fraction, and multiply. Any questions? So it was very humbling. It was a very humbling experience to realize, like, I don't have a good answer to that question. When we sum this up, what is left on the left side? What remains on the left side? Very good. So we have 4 carbon left. Those are solid. We have 5 hydrogen gas molecules left, or 5 moles of hydrogen gas, more accurately. Is there anything else on the left side? They have all been removed. They've all canceled. What about on the right side? What remains? C4H10. And that is a gas. When we sum all of the delta H's, what do we get? Negative 125.6 kilojoules. And so we can tell ourselves some interesting things. If we were somehow able to take solid carbon and mix it with hydrogen gas and make butane, which again will never happen, but if we could make it happen, how much energy would be released or absorbed by a mole of that? By 4 moles of carbon reacting with 5 moles of hydrogen. How much? How much energy would be released if I took 4 moles of carbon and 5 moles of water, or of hydrogen? 125.6. And it would be, I mean, I've already spoiled it. This is going to be my next question. It would be exothermic. It would be released. If I put a thermometer next to this reaction, what would happen to that thermometer? Yeah, I mean, thermometers don't measure joules, they measure temperature, so we don't know what it would go up to, but it would definitely go up. It's going to increase the temperature by whatever 125.6 kilojoules is able to do to that medium, which would depend on what's around it, right? This would affect air differently than it would affect water, and it would affect a lot of water differently than it would affect a little bit of water, right? But no matter what, the temperature would go up. That thermometer would raise if you actually have like one of the old-fashioned red dye thermometer. Questions about that? Or if you have a mercury thermometer? Yeah, I have a little mercury collection at home. It's a bad idea, but it's sort of fun.
How many kids do you have? You have 3 kids, right?
Yes.
That's a terrible idea.
Listen.
Survival of the fittest, you just leave them around your house.
No, of course.
There used to be 5.
Like I also have a chainsaw at home, but like that doesn't mean my kids are playing with it. And like we have like electrical sockets, but like that's safe because we, you know, put systems in place when the children are young to make sure they don't put things in them. And at this stage, if they did, that's on you, kid. I said the old ones. Obviously, the young ones. No, and let me tell you, like my brother-in-law and I were renovating his basement, and it was one of these things where he thought I had turned the breaker off. I thought he had turned the breaker off. So I was up wiring an electrical box, and all of a sudden, got me, right? Like just right through me. And I'll tell you, if you haven't had 120 volts through you, I encourage you not to, because it is really unpleasant and it hurts. And it gave me a start. But I learned something, which is don't trust Kevin to turn the breaker off. You turn the breaker off. Because Kevin's not the one who's got his hands in the electrical junction box. Now is he? All right? There's a lesson in there.
So you basically got electrocuted and then...
So I have put a bunch of practice questions on here. Listen to me, look at me. This stuff is not going anywhere. And if you haven't intuited, what we're going to do next is take this and combine it with the stuff we did before, where you also have to do some stoichiometry. All right? It's not going anywhere. So you have two choices. There are two paths in front of you. And down this path lays going, fiddle-dee-dee, I'll think about it tomorrow, a la Scarlett O'Hara. I'm just not going to do my homework and hope for the best. And down this path lies comfort and wisdom and finding all of these really easy because you've done a bunch of them. All right? Look, do this homework. Go back and do yesterday's homework. These need to feel intuitive to you. You can't play and sing the banjo at the same time if you're thinking. You can't sing and play the banjo at the same time if you're thinking about singing and playing the banjo. Does that make sense? You cannot do it. Your brain is not capable. One of the two has to be intuitive. The singing has to be happening on autopilot, or the banjo playing has to be happening on autopilot, or both of them. But you cannot concentrate on both. That's how a skill works. It has to be muscle memory. If a hockey player had to stop to think, okay, the puck is coming in. I'm going to put my stick down and slowly move it back so I can slowly receive this pass. The pass is already whizzed by him. It only works as repetitive memory. That's how our brains work. You will only be able to do problems that use these skills if these skills are instinctive for you. And that only happens if you practice lots. It does not happen if you have gone through the 3 examples we did in class together and said, yeah, that makes sense. It doesn't work. I wish it did. I would love it. If there was some magic button I could push where I could show you 3 times and you would go, hey, I get this. I can do it forever now. It doesn't work that way. If you went to basketball practice, watched the coach do 2 layups, did one with him watching and maybe guiding your arm, and then said, okay, I'm good at layups, and never did one again, you're not going to make the basketball team. All right? It doesn't work that way. You are not going to only do the 3 examples we did in class and understand thermochemistry. It doesn't work that way. Do your homework. If you're not sure how to do it, come get help. If you hate me and you're hiding it during class time, but you just don't think you can hide it for another 10 minutes, get help from Mr. Smith or Khan Academy or one of your peers. Do your homework. You need to. All right? You will not learn this otherwise. End of rant.